is CPU is roughly 100 times faster than main memory. So if you remember a pipeline execution diagram of CPU, it works like this. So assume that CPU is running at 1 gigahertz, right? 1 gigahertz, then clock period is 1 nanosecond, right? And main memory, that means main memory takes 100 nanoseconds to access, to read instruction, to read the data. That means, in other words, it takes 100 clock cycles to read the instruction from memory and to read data, to access data, right? So if you draw a pipeline execution diagram, it looks like this, right? Instruction fetch, it takes 100 clock cycles. CPU is doing nothing, just wait until instruction is coming in. Right? And then once you have instruction, then CPU can do decoding, execution, and so on. Right? To read next instruction, CPU should wait another 100 clock cycles, right? So that pattern goes on and on. Then effectively, CPU is able to execute one instruction in every 100 cycles. That is too bad, right? CPU is doing nothing, just to wait until instruction comes in, just wait until data comes in. That is too bad, right? So that is why we want to have small but super fast internal memory inside the processor. Small but super fast internal memory between CPU and main memory. And our hope, it is not guarantee. Our hope is CPU can find instruction and data from the cache. That is our hope. It is not guaranteed, but that hope is most of the time true. More than 90%, 90. More than 90% of the time, that hope is true. You can find data, you can find instruction from the cache. So cache is able to provide instruction and data to CPU. Okay. So pipeline execution diagram looks like this. Cache takes hopefully 1 clock cycle if cache can be accessed in 1 clock cycle. Cache access time. You assume that cache access time is just 1 clock cycle. So that pattern, we want to create that kind of pipeline execution diagram by placing cache between CPU and main memory. So that is this one. Let's move on. Okay. So cache is designed SRAM technology, not DRAM, right? Main memory is designed with DRAM, and caches are designed with SRAM, different memory technology. So that is the thing. And caches are located inside processor, right? That is our desktop computer block diagram. So inside the processor, we have caches, right? So examples are, for example, Core i7, more than 10 years old Intel processor. Okay. Take a look, Core to Duo, right? 2 CPUs, and right? Roughly half of real estate, silicon. So a little bit, roughly half of the real estate is dedicated for caches, right? L2 cache and level 1 caches. And how about Core i7, right? Core i7, you have 4 CPUs, right? 4 CPUs, and then big level 3, cache. That is a shared cache, shared by 4 CPUs. And inside each core, you have level 1, level 2 caches, private caches. Right? So inside each core, you have level 1, level 2 caches. Those are private caches, private to CPU. And L3 cache is shared by these 4 CPUs. Okay, but if you have any question, please interrupt me. Okay. and Sandy Bridge. I was involved in this project when I was working Intel. This is my CPU. 4 CPUs and level 3 cache. Okay? And inside each 4, again, level 1, level 2 caches. Third generation, let's move on. This. Okay, let's read this. This one, please. Okay, so who is managing data transfer? Okay, between you have to think about assembly programming. In assembly programming, you have CPU and memory, and many different IO devices, right? So from programmer's point of view, you have only 2 components: CPU and memory. Your program is located. Your program is placed in memory, right? Your program is what? Code and data, right? With your code, you want to process this data. That is your program, right? And cache is placed between these 2. And who is managing data transfer between these? What do you think? Hardware. Okay. Cache is transparent to you. You don't have any control. You don't have any control of caches. Right? That is automatically managed by hardware. That hardware is called cache controller. Cache controller is managing data transfer and also that data transfer. So CPU is requesting data by executing LW, memory read, right? Or memory write instruction. You are requesting that write data, right? Then based on that address, cache controller is looking up the cache. Okay. If data is found in the cache, then cache will provide the data. If data is not found in the cache, then cache controller automatically access main memory and place that data into the cache. Supply the data into CPU. The point is, it is transparent. There is no cache from programmer's point of view. You cannot do any operation, any data manipulation. There's nothing. You have only CPU and main memory. That's it. Right? And caches are automatically managed by hardware. Okay. So cache, between cache and main memory, that is automatically managed by hardware. Right? So you have a register, right? When you write program, you have registers, right? General purpose register. In ARM, you have R02, R15. Right? So you are loading some data into some register, right? And writing some data into some memory location. So CPU and memory. That's what you can see. Okay. Cache is ghost, transparent. Okay. Okay, let's move on. Then cache is super tiny compared to this is important. Big picture first, right? If you think about your computer system, main memory is typically how big? 8 gigabyte or 16 gigabyte? Roughly that size, right? How about cache? How big the cache is? If you think about level 1, level 2, level 3, then that is like 8 megabyte, roughly. 8 megabyte cache. So the unit is different. Megabyte, gigabyte. Roughly 1,000. 1,000 times smaller than cache size. 1,000 times smaller than main memory. Then I told you, right? Our hope, right? Our hope is what? You can find the instruction. You can find the data in the cache. So how is that possible? 1,000 times smaller. Then chances should be 0.1%, right? Simple math. So 0.1% of the time you can find the instruction from the cache or data from the cache, right? But more than 90%. How come? Because your program has some special properties. That is called localities. Your program has localities, right? This one, your program, my program, everyone's program has that characteristic. This one, Soki. Okay, so two characteristics that is super important. Okay, temporal locality and spatial locality. So what is temporal locality? In Korean, 시간 지역성. Okay? Temporal locality means if you access, let's say using load instruction, if you access some memory location R1, let's say R1 is 1000 in X. So if you access this one location, this specific location, then it is very likely to access same location again and again in the near future, in the very near future. You access this location, okay, using a load instruction. Very high chances of accessing same location again and again in the very near future. That is temporal locality. And spatial locality in Korean, 공간 지역성. Okay, what does that mean? 공간 지역, spatial locality means if you access this location, very likely to access each neighbor. Each neighbor. 1004, 1004, 1008, and FFC, each neighbor in the near future. That is spatial locality. Okay, so probably you are curious, really? Okay, let me show you the code. Take a look at that code. Simple. Simple C program, right? You want to what? You have array, 3 arrays. Right? Each array has 100 elements. Right? So and t. So in this code, you want to do some multiplication of each element, then add t. Can you tell me which local variable is local variable has spatial locality, and which local variable temporal locality? First, temporal locality. Which variable is showing temporal locality characteristic? What is temporal locality? If you access one memory location, very likely to access same location again, right? D, right? You are accessing D 100 times, right? So 100 iteration, you are accessing same local variable again and again. Right? How about I? This loop count, I. You are accessing that I, many times, right? Same variable in the near future. Right? How about spatial locality? What is spatial locality? Access one location, specific location, very likely to access each neighbor. So array, right? A, B, and C. So first iteration, you are accessing A0, B0, C0. Next iteration, A1, B1, C1. So next location, right? Next iteration, A2, B2, C2. So you are accessing each neighbor, right? So that is why cache is working, right? So when cache miss happens, cache controller will place not just the data you requested, but bunch of data into the cache. Okay, so cache line size data. So let me explain cache structure now. Any questions so far? So very simple. Some example. There are three, different cache structures, right? The most simple one is what? Direct map cache. Direct map cache. Let me explain the cache structure of direct map cache with this, I think. Okay. Let's say you have 64 kilobyte cache. 64 kilobyte cache. And direct map cache, if I go, you have tag, field, and data. And each row, that is called cache entry. So cache is composed of many of cache entries. First cache entry, second cache entry, cache entries. Then typical. So data. This is the place where the place where you load data. This is data. The place the load of data, and this one is called the cache line. Cache line. And the cache line size, typical cache line size is 32 byte or 64 byte. So Intel is using 64 byte, and the Cortex A9 we are using has 32 byte cache line. So that means once cache miss happens, this whole memory block. So 32 byte or 64 byte. This one is called memory block. Memory block will be placed into the cache line. So let me draw. So main memory is logically divided into cache line sized chunks. So from location 0, whatever the location is, then this main memory is not physically, logically divided into the cache line sized chunks. So let's use 64. It means logically divided, right? The first 64 byte, then second 64 byte, third 64 byte, and so on. Okay, so this one is called memory block. Memory block. Then 64 KB. Then how many cache entries you have in this case? 64 byte each. And how many cache lines you have in 64 byte cache? 64 kilobyte divided by 64 byte. Then 1K. That means you have 1024 cache entries in this cache. And the tag is the place where you record location information. So in case of cache miss, you are executing LW instruction from location, whatever it is, right? Let's say this memory block. You are accessing some data in this memory block. Then at the beginning, cache has nothing. When you turn on the computer, cache does not have anything. So cache miss happens. Then this whole memory block, the memory block containing the data you requested, and assume that you are requesting this data. There's the location of R1. Okay, and this whole memory block containing the data, this whole memory block will be placed into the cache. Not just this one data, but this whole memory block, 64 byte whole memory. Then where to place this memory block based on the address. Right? Let's say the address. CPU generate, right? 32. Let's assume CPU is generating 32-bit address. Okay. Then each cache line size is 64 byte. So we are not using last 6 bit. So to the power of 6, that is 64. So last 6 bit is used to pinpoint. So among these 64 bytes, which one do you want to access? Okay. So that is used. That is called offset. Okay. And next 10 bit. It is specific example. Right? Next 10 bit is used to index the cache. Index means to select specific cache entry. Okay. So depending on this 10 bit, right? 2 to the power of 10, 10,024. So using this 10 bit, you are selecting particular cache line, and that cache line will be selected, and tag information will be compared against the remaining of the. So these two are equal, then we say there is cache hit. Cache contains the data you have before. So there is indexing. That is called index. So using this 10 bit, you are indexing. You are selecting particular cache entry. Then tag information will be compared against the remaining bits. So in cache terminology, we use this cache. We use this terminology: set number 0, set number 1, set number 1023, 0 to 1023. So in other words, using this index, you are selecting particular set. 집합 in Korean, right? 집합. So in direct map cache, you have only one cache entry in one set. Again, you are selecting particular set. In direct map cache, you have only one entry. Okay, for comparison. That is cache structure, the most simple cache structure in cache operation. Any question about this? Yes. Okay. Question? Say again. Depending on compiler, the question is, A, B, and C, right? The 100 element. So I don't know, but I don't know. You can compile the code. So array, right? Array A will be located in consecutive memory locations, starting from A0, A1, A99. How about B? B is located right above that A99. I don't know. But probably not. Right? So probably some boundary. I don't know. You can check out the compiled output of B0, B1, and B99. I don't know. There is a gap, some gap between these A and B, or consecutive. I don't know. Check out the compiled binary, the symbol table. So depending on the number of elements, I think. Number of elements. I don't know. Any other questions? Okay, let's move on. There is one. Then okay, this one. me explain. So write allocation policy. Read operation is very simple. Right? When it comes to memory read, right? If you miss the cache, then the memory block containing the requested data. You are requesting this data, right? That memory block containing requested data will be placed in the cache. And the data will be supplied simply. Very simple. But how about write operation? You are executing store instruction. LDR in ARM, right? LDR, STR, store instruction. R0, then R1. Okay. What if you execute store instruction? Okay. So we are assuming you are executing two store instructions. And I'm trying to explain write allocation, write back policy. So assume that this cache is implementing these two policies. Then let's say you are executing store instruction targeting that memory location 1208. That is 1208. You are writing some data, okay? Some data to that location, and it happens to index. Let's assume it happens to index that cache entry, and it happens to select that set because of that index. Let's assume that. Then we have a cache hit because the tag information is equal to the remaining upper bits. So we have a cache hit. And what happens is in write back policy, the data will be written only to cache, not main memory. Main memory will not be updated. Okay. So we want to avoid memory access because memory access is so slow. I don't want to access memory. Okay. So eventually the data will be written back to main memory, but not now. Okay. For now, I'm going to update only cache. And then to indicate only cache is updated, there's a dirty bit. Dirty bit is set to 1. Okay. Then next, you are executing another store instruction. And another store instruction R2 and R3. That R3, we are assuming there is no 04, location 04. Okay. Then it happens to select that set, that cache entry. Then there's no data, right? So then what do you think should happen? We have a cache miss. We have cache miss. Then what happens is, according to write allocation policy, you have to allocate memory block into the cache first. Allocation first. So read the data containing that memory block, right? So that is the data you are looking for, right? You are trying to update that memory location. So that full memory block will be placed into that cache entry. Okay. Then tag information is recorded based on that address. Okay. Then we loaded that memory block into the cache, then update the cache. Right? According to write back policy, we update only cache and main memory. So this data R2, the data will be written to that particular data section, and the dirty bit will be set to 1. Indicate this cache entry is dirty. Eventually, you have to update main memory with the data. That is write allocation and write back policy. That is typically used in computer. Write allocation and write back. How about the other policy? Write no allocation, write through policy. Same scenario. We are executing these same two instructions, right? First instruction, you are indexing. You are selecting that cache entry. Then you have a cache hit. Then write through policy means through, right? You are updating both cache and main memory both. Right? So you don't need 30 bit. So in this cache, rise through cache, you don't need 30 bit, right? Because your main memory is updated all the time. Okay? All the time. Then second store instruction. It happens to index that cache entry, and you have a cache miss. It doesn't have any cache miss. Then what should happen? Going to write through, no allocation policy. No allocation. You are not allocating. Right? You're not placing this memory block location. You are not doing that. Right? Just update. Maybe. So that policy is not that used. This policy sometimes provided. You can select. The policy you want to use, but people usually use this policy, right allocation and right time policy, because main memory is so slow. I don't want to touch main memory. Okay, there's the one. Then let's move on to next PowerPoint cache number 2. 지연? Okay, so I just explained the dynamic cache, and there are two other cache structures: fully associative cache and set associative cache. Let me show you some examples. The reason why we use different cache structure instead of using dynamic cache is because dynamic cache hit rate is pretty low. Meaning that there are not that high chances of finding data in dynamic cache. If you use a set associative cache, that hit rate, the probability of finding data will be higher. That is because you want to use different cache structure. So this one is a dynamic cache, right? So cache entry number 0, cache entry number 1, and so on. In other words, set number 0, set number 1, set number 7. In each set, you have one cache entry, tag and data. And this one is structure of two-way set associative cache. Two-way, right? Two-way set associative. Same size the cache, right? Same size. You have two. So way number 0, way number 1. So set number 0, here set number 6. Set number 6. Data. So using index, you are selecting particular set, and in that set you have two candidates, two cache entries to look up. So if you select this particular set, and that these two cache entries will be compared against the upper address to check all this. 4-way set associative. Then you have 4 cache entries in each set. In one zip top you have 4 one-shot, right? 4 1-shot, 2 1-shot, right? 2-way. Right? Fully associative cache. Okay, the last one. Fully associative cache, you have only one set. Okay? So you have only one set. You always select that whole cache, in other words. So in that set, you have how many? 1, 2, 3, 4, 5, 6, 7, 8 cache entries. So in this case, fully associative cache, different name is 8-way set associative cache. That is different name in this case, in this particular case. Okay. And set associated cache example. Example 16 kilobyte cache. 16 kilobyte cache. So that means 4-way set associated, right? 4-way set associated, and we assume cache line size 4 byte. So that is not realistic. That is not realistic cache instruction. Because cache line size, right? 4 byte means that what? Means that cache miss happens, you are loading. You are loading only one, right? One word. You can not in this big memory block, right? That means you are not exploiting what? Spatial locality, only temporal locality, right? Because cache is loading only the particular word, right? Not its neighbor data. Because cache line size 4 byte. So that is not realistic. No one is designing the cache like that. So let me draw a little bit more realistic. Right? Same size cache, 16 kilobyte, and assume that 64 byte cache line. That is realistic. So that means what? 4-way set associative. You have 4 ways. Way number 0, way number 3, and tag data. Data, string tag, and data. Your set number 0, and this cache line size 64 byte, right? 64 byte, 64 byte. 64 byte and 64 byte. And 16 kilobyte. So that is 4K byte. So first way 4K byte, 4K byte, 4K byte, 4K byte. So 60K. You add up, right? 4, 4, 4, 4, 60. Then how many sets do you have? How many sets? 4 kilobyte divided by 4 kilobyte divided by 64. Then what is that? How many sets? To the power of 12, to the power of 6. To the power of 6 right there. I mean 64. So you have 64, right? That number 63. You have 64 different sets. Okay. So then 6-bit offset, same 6-bit offset because cache line size 64 byte, right? 2 to the power of 6, 64 byte. So then, how many bits you need to use for indexing? 64 different sets. So you use next 6 bit for index. Select particular set. Okay. So once particular set is selected, let's assume that set 0 is selected for lookup. Then this tag information, 4 different tag informations will be compared against the remaining upper. So that is one. So in this case, you have how many? 1024. 1024 different sets. Because cache line size is 4 bytes in that example. So you use 10 bit to select particular set, then 4 cache entries. 4 cache entries inside the set will be selected for lookup. Okay. So the tag information is coming out. I'm talking about hardware operation, right? Tag information is coming out, and that is compared against the remaining of the bits. So these two are equal. Okay. These two are equal. Then valid bit is set to 1. Valid means that entry is valid. Then for that cache hit. So one of the ways contain the data you are looking for only. So we call that cache hit. The data, if data is coming out also using this 4x1 multiplexer, box is selection, right? Using this multiplexer, you are sending data to CPU. So using that hit information, multiplexer, you need a control signal. Selection, right? Control signal. Right? Which one do you want to select? First data, second data, third, fourth, right? That is controlled by selection. Right? That is cache structure. Set associative way. Set associated cache structure. Any question about this? Okay, let's move on. Then the question is, why set associative cache is better than direct cache? That is probably obvious question. Right? In terms of hit rate, I told you, right? If you change, say to the same size cache, if you change cache structure from direct cache to two-way set associative into fully associative, then hit rate will be higher. For example, direct cache 80% hit rate, a fully associated cache 95%. The hit rate goes up. It is not that intuitive and clear to explain, so you can. I like you to follow this, that example. Then you can get some idea why associative caches are better in terms of hit rate, right? Probability of finding data in the cache, hit rate, right? So I like you to follow right this one. But if you think about this fully associative, right? Fully associative is extreme, right? You have only one set, right? Dynamic cache, right? Think about dynamic cache, fully associative. Dynamic cache, let's say you have 8 entries, right? Set number 02, set number 7. And fully associative, you have only one set. Set number 0. You have 8 tag, data, tag. So in dynamic cache, you are selecting only one particular set for lookup. Right? That set will be compared. Right? And if while executing your program, what if multiple blocks? So this block, because you are executing some memory access instruction, right? LW, SW. What if multiple blocks are mapped to the same entry? Multiple blocks are competing to go into the cache entry. Then what do you have to do? You have to kick out. Okay, you have to remove. You should be removed. I need to replace new memory block. That can happen. But if you have set fully associative, that whole set is selected, right? Then compare. Everything is compared at the same time. Right? So these many different multiple blocks can be placed here and here and here. So you don't have to evict, you don't have to remove that guy. So I like you to get some feeling, get some sense why full associative caches. So in between you have set associative cache. In the middle. Dynamic cache is one extreme, fully associative cache the other extreme. So by thinking about fully associative cache operation, you get some sense. Why? That is reduced, that is improving hit rate. It is improving hit rate. Try to think about that. That is one. Then one last thing. So that is the one. That is the one. A computer architect came up with. Computer architect ran some benchmark programs, many different application programs, right? And that is the result they got. The 4 kilobyte cache, the green, 8 kilobyte cache is sky blue, and 512 is okay. And then different cache structure. One way means direct map cache. And then 8-way set associated cache. So miss rate goes down, tends to go down. As you increase associativity. In other words, hit rate goes up as you increase associativity. Replacement policy, that is probably you need to know, right? So in case of direct map cache, if you have a complete meaning that two memory blocks are mapped to same location, same cache entry. You have a complete. Then there's no choice. You have to remove that guy and place new memory block. How about set associated cache? It's a set associated cache. You have cache miss. Assume that you are indexing this set 0. Okay, all these cache entries are selected for lookup. Set 0, right? These 4 will be compared. Then you have a cache miss. Then which one you want to remove? This one? This one? Which one do you want to remove and place new memory block? You want to remove this guy and place new memory block to here? Or remove this guy and place new one? Which one do you want to remove? Hey, what do you think? What do you mean by that? Okay, there's the answer, right? In the PowerPoint. What is that? Yeah, right. Yes, the oldest one, right? Oldest one. In other words, least recently used, right? LRU, least recently used. So you need LRU bit. Those how many is it? 64. Right? You need same 64 LRU bits. That is recording which cache entries. Which cache entry is the oldest one, and which is the newest one. So you want to, let's say, while executing your program, right? Memory block is placed. First, memory block is placed here. And second, memory block timeline. First memory block, second memory block, third and fourth and fifth. You are loading 5 different memory blocks, the same set. Let's assume. Okay. The first memory block is placed here. Second memory block is placed here. Third one here. Fourth one here, and fifth one. Right? Fifth one, it is fully occupied. Then you have to sacrifice one guy. You have to kick out one guy and place that block. Right? And which one do you want to kick out? Probably this one, because that is the oldest one. You want to kick out this guy and place a new memory block 5. Then how do you keep track of that order, access order? This is the oldest one. This is the newest one. you need to design one. Digital logic, right? Remember finite state machine. Digital logic, right? Finite state machine. I think we have time. So you have to, okay, let me quickly, because that is somewhat important. LRU. So you have to keep track of this, right? Way number 0, way number 1, way number 2, way number 3. Then way number 1, 2, 3. Then 2, 3. I mean 1, 3. And then 3, 2, 3, right? 1. And so on, right? So that is the access order, right? Time. So let's say this one is state 0, and this one is state 2. State 0 means this is the oldest, and that is most recently, or that is least recently accessed, least recently used, accessed entry. And this one is most recently used entry. Okay. So in S0 state, you have cache miss, then you want to replace the cache entry in way 0. Cache entry in way 0. So in this case, what if you have cache miss in S2 state, right? S2 state, same thing, right? The cache entry in way 0 is the oldest. Cache entry in way number 2, that is the latest, okay? The most recently used. So same thing. So you have to replace that. Right? So you have to record that, that information, right? And how many different states you can have, right? So 4, 3, 2, 1. So 4 factorial, right? 4, 3, 2, 1. So 24 different states. S02, S3, 23. So you need to draw this state machine. S02, S1, S2, 24 different states, right? Depending on access pattern, you move. That is state machine, finite state machine, right? So from digital logic design, right, you know how to design FSM. So that is LRU. But LRU algorithm is too expensive to design in real hardware. In full-way set associative, probably you can do it, right? Because there are only 24 different states. But it's a state diagram is very complicated. But think about 8-way set associated cache. Right? 8-way. Then how many different states? 8 factorial, right? About 16-way set associated cache. Then 16 factorial. Then many states. Let me do. Quick computation. So 8. Where's that? Here. So 40,000 different states. You don't want to design, right? And then how about 16-way set associated? 1, 6 factorial. See? How do you read that number? I don't know how to read that number. Right? Then many different states, right? So you don't want to design LRU, right? True LRU. Simply too expensive. Probably LRU hardware is more, LRU hardware is bigger than actual cache. I don't think it is works, right? So, people use a pseudo LRU. People use pseudo LRU or simply randomly pick cache entry. Okay, there is one. Then the last thing is multi-level cache. Multi-level cache. Why do you want to have multi-level caches? That is the block diagram of multi-level caches. So here you have 3 levels of caches, right? Level 1 caches, 2 level 1 caches. Those are split caches. Level 1 instruction cache. Instruction cache means it is holding only instructions, right? Code, your code. And data cache, it is holding only data, code and data, right? Your code, instructions, and data. So split cache, we call that split cache. And L2 cache is a unified cache. It is holding both instruction and data, unified cache. Okay? And L3 cache is also unified. And to compare the size, 32 kilobyte, that is typical size. 256, 8 megabyte caches. The question is, why do you want to have these multiple levels of caches? How about one big monolithic cache? What would be the problem with one big monolithic? Because time, yes, right. So here you have CPU, and one big monolithic cache, let's say 8 megabytes, and main memory 8 gigabytes. Okay? So that is cache. The problem is this big cache is access time. Cache is big, then it takes too long time to search the data and provide the data to the CPU. Roughly, it takes 30 clock cycles in the real machine. 30 clock cycles in 8 megabyte cache. Then CPU, doing nothing for 30 clock cycles, just waiting, right, to get data and instruction. So it is not the solution. But the good thing about big cache, if cache is big, what is good? What is good thing? Cache is big. Hit rate, right? There are higher chances of finding data and instruction, simply because it is able to hold more data and instruction. Right? Big, right? It can hold more, right? You don't have to kick out. Okay, you don't have to kick out. It has enough room to to place new memory blocks. Right? Again, so hit rate would be very high if cache is big, but the problem is access time. It's access time. Even though you have a hit, the data is found in the cache, instruction is found in the cache, it takes simply too long time. CPU should wait. That is why the computer architect, computer manufacturer design these multiple levels of cache. So level 1 cache is very small because level 1 cache, important thing is access time. You have to supply data and instruction to the CPU as fast as possible. 2 bits. CPU, right? CPU need instruction and data, right? You have 32 kilobyte iCache and data cache. I want to CPU, right? CPU is running super fast, right? CPU need instruction, CPU need data. Using the small cache, access time is very small. So I want to cache. My CPU want, it is feeding data and instruction to the CPU, right? Hopefully in 1 clock cycle. But if you miss the cache, then you have a backup plan, a level 2 cache. You have a level 2 cache, a little bit big, 256 kilobyte cache. Right? And there is backup, right? Level 1, you missed a level 1, then check out level 2. If you miss level 2, then check out level 3. Level 3 cache. This one is called last level cache. The last level before main memory. So if you miss LLC, then there's no choice, right? You have to access main memory. That is going to be a disaster. Disaster. It takes too long time, right? So then so you understand the size, right? Cache size. And how about cache structure? What kind of cache? If you are a computer architect and you are hired by Intel, AMD, and ARM, then your job is designing cache architecture, cache structure. So what kind of structure you want to use for level 1? what kind of structure you want to use for level 3. Level 1 cache, we want to use low associativity, direct map cache. Direct cache. But you know, direct map cache is good in terms of what? In terms of access time, because you have only one entry for lookup. So hardware is very simple. Check out one specific set. In that set, in direct cache, you have only one cache entry, right? One cache entry for lookup, right? So you read tag information and compare that against address. So hardware is very simple. Hardware is simple means access time is very simple. How about set associated cache? You are selecting multiple cache lines, right? In one set, you have multiple cache lines. Those multiple cache lines should be compared at the same time. And finally, go through multiplexer. One of them is going through multiplexer. So you need additional hardware. That means it takes time. Okay. So direct map cache is good in terms of access time, but the bad thing is what? Hit rate. Hit rate is low. So you have to do some juggling, right? So the hit rate access time, right? So typically people use set associative cache with low associativity, like 4A set associative. So here, last level cache, what would be the important factor you have to consider? Which one? This one is important or access time is important? Which one? Hit rate is important, right? Access time is not that important. Why? Why is that? Because this big cache is already too slow, right? Already slow, right? And it takes 30 clock cycles. Okay, 31 clock cycles is not that different. It's not a big deal adding one clock cycle more, right? But if you miss the cache, disaster, right? Access main memory access, right? So to improve this factor, hit rate, you want to use high associative cache, like 16 set associative, 32 set associative. So there is one. Okay. There is one. I want to finish cache lecture today. That's why I'm going to be pushing hard. Okay, that is about caches. Okay, I'm done. Okay. Okay, then let's talk about the real example. Real example in our Cortex A9. In Cortex A9, this is the block diagram. You have two ARM CPUs, right? ARM2, 1 and 2. And each CPU you have instruction cache and data cache, level 1. It's pretty. Level 1 data cache. And then our level 2 cache, 12 kilobyte level 2 cache. That is shared cache. That is shared by two CPUs. It is serving two CPUs. And also unified cache level 2. So if I draw a block diagram, it looks like this. Cortex A9, right? That is generating address. We haven't studied TLD yet. Translation outside local. That is the topic we discussed from next week. We will talk about that probably 2 weeks from next week. So for now, don't worry about that. Don't worry about this. And instruction cache, data cache is accessed with some address. This one is called virtual address. And PA means physical address. TLB is actually translating virtual address. Take this one as an input and generate physical address. Virtual to physical translation. Okay. But for now, don't worry. So caches can be accessed with virtual address or physical address, depending on hardware structure. Then level 2 cache, unified cache is accessed with physical address. Caches are accessed with some address. virtual or physical. Sorry, kilobyte iCache, 512 kilobyte. And this one, 성주. Yes. Okay, thanks. 32 kilobyte Revera cache, right? Revera cache, 32 kilobyte each for iCache and eCache. And cache line size, and this cache line size. Cache line size 32 bytes. 32 bytes in that case. Intel 64 bytes. Intel, your computer. And cache structure 4-way set associated, right? This one 4-way set associated, and each cache line 32 bytes. So if you miss the cache, 32 byte memory block will be placed into a cache. A replacement policy, right? Round robin or pseudo random. And critical word first means you are requesting this particular data, but cache line size 32 byte, 32. Right? Then is reading the data you requested. The data you requested is critical data. Why critical, right? Critical, that's critical because your CPU needs that data, right? You want to supply that data first, right? To CPU. CPU needs to execute, right? The program, right? So critical data first, the data you requested, and its neighbor later. So critical data will be supplied first. Then level 2 cache, let me do this. Level 2 cache, 512 kilobyte. Same line size, right? Same size. And associative 8-way sub associated, a little bit higher associative. L1 4-way, L2 8-way. Right? Multi-level cache, right? Multi-level cache, right? So that in the last level cache, if you miss the cache, disaster, right? So that's why you want to use high associativity. Replacement policy, random critical first, and so on. So last one, okay, don't worry about this. If you want to know about this, then join graduate school. We don't have enough time. Okay, and then let's talk about some programming. I told you, right? Caches are transparent. It is a ghost, right? It is not visible to you. It is transparent. You cannot do anything. But there is a limited operation you can do, like cache on or off. You can turn on the cache or turn on or turn off the cache using that system control register. Using this IB, if you set this IB to 1, iCache enable. You are enabling instruction cache. By default, cache is not enabled. In our Cortex-A9, cache is not enabled by default. So you have to enable the cache if you want to use that. Right? And see, you can data cache enable, eCache. So that is enabling level 1 cache, iCache and eCache. And then one more register you have to touch. That is a system control register. That register is accessed with, if you remember VBAR, right? Vector base register in interrupt discussion or vector table. We use MCR instruction to update this system register. Right? Same thing goes to system control register. To update this system register, you have to use MCR instruction. So MCR to update. And then one more thing for level 2 cache. Let's skip this. Okay, so this is an example. To enable instruction cache and data cache, you use MCR instruction. MCR, then the data, data is what? 1004. Why 1004? You go back. If you go back, I bit is in 12th bit position. So 1, right? There is 12th bit position. Hex number, right? And then C bit, second bit, 4, 100 in binary, 100. So you want to touch the C and I bit. Okay, set those 2 bits to 1 to enable, right? So if you look at the manual, then our manual is providing this instruction. Okay, you have to simply use that instruction, MCR, R0, here R0. Before you use this instruction, place this data in R0, then execute this MCR. Then cache will be enabled. Or, okay, skip this. Level 2 cache. For level 2 cache, you have to touch different register. So L2 enable, right? L2 enable. 0 level 2 cache is disabled, 1 enable. Which register? Reg1 control. Reg1 control is Reg1. Okay. So 2 places. So let me show you a demo. It is very simple demo, and I posted new assignment. Assignment 8. It is super simple, really. It takes 5 minutes. Really. Cache on or off. Okay. So let me show you a demo first. You can download which one? This one. This code. Caches. Okay. I already created this project for you. And first one, I'm disabling. I'm touching this L2 register. Okay, disable level 2 cache, and using MCR instruction, the instruction I just told you, and 4096 and 4, right? This one, 130, 4096 and 4. So I'm trying to turn on level 1 cache. Turn off, sorry. Disable, because I'm using bit clear. Bit clear. That bit will be 0, not 1. Right? Bit clear. So I'm going to run this code, disable cache, and next I'm going to turn on. This is commented out now, but I'm going to turn on this one, enable cache, and jump to main, right? C code. C code is doing what? C code is just simply toggling LED, and that is a loop count. Okay. So let me first execute the code with cache disabled. Okay. Here, caches. Okay. Okay, so F5, then disable the cache, level 2, disable level 1, then jump to C code, and let me press F8. Okay, check out this LED, toggle time. It's LED. Roughly 1 second interval. 1 second with cache disabled. And let me change the code. Disable, okay, comment out this code and make it active. Okay, enable now. Okay, enable the cache. Compile this code. let me download. Save. Okay, now at 5, then enable, right? Enable caches, then jump into C and press F8. See the impact? Super fast, right? Compared to the previous one. Very fast. Okay, that is for today. Any question? Okay, see you. I'll see you next Tuesday.
프로젝트 과제에서 궁금한 게 이제 IAR이 있고 프라이빗 타이머면 9번을 그릴 거 아니에요. ISR에서 트럭스 디바이스 아이디를 가져오잖아요. IAR에서 관련 이제 9번이 아니면 뭐 어떻게 해야 된다 그런 건 해야 되나요?
인터럽트가 타이머에서만 발생하죠. 다른 데 발생하는
다른 건 고려할 필요 없어요. 하나 더 있는데 ISR에서 IAR을 있고 이제 뭐 이거는 로직 처리를 하고 그다음 EOIR 쓰잖아요. 그거에 대한 순서가 그렇게 정해져 있는 거예요, 아니면?
당연히 먼저 IAR을 읽어야 되고 먼저. 네. 그 다음에 마지막에 end of interrupt register를 업데이트를 해야만 CPU 인터페이스에서 이제 하드웨어가 아 끝났구나, 이런 처리가 끝났구나라는 걸 인지하고 이제 다른 인터럽트를 보낼 준비를 하는 거예요.
그러면 만약에 ISR에서 컨텍스트 스위치를 먼저 한 다음에 그다음 IAR을 있고 그다음 EOIR 쓰면 이렇게 해서 구현했긴 했는데 그러니까 맨 처음에 컨텍스트 스위치를 하고
컨텍스트 스위치로
그러니까 CPU 만들어서 이제 바꾸잖아요. 테스트를 교체하잖아요.
테스트 교체를 하려면 인터럽트가 일단 걸려 있잖아. 걸려야 거기서 이제 컨텍스트 스위칭하고 하는 게 맞아요.
ISR을 진입한 다음에 진입하고 이제 처음에서 스택에 넣고 이렇게 한 다음에 그 다음에 컨텍스트 스위치를 하고 그 다음에 ISR 읽고 그 다음에 EOIR 하는 식으로 구현했거든요. 코드는 그렇게 짜서 돌아가긴 돌아가거든요.
그리고 어떻게 들어간다? 인터럽트 걸리면 점프하는데 ISR로 점프하는데 거기서 컨텍스트 스위치를
먼저 한 다음에 그다음 IAR을 읽고 그다음 EOIR 쓰는 걸로 구현을 해서
근데 이게 로직적으로 그러니까 지금은 너무 간단한 시스템이기 때문에 네. 어떻게 구현하건
약간 이상할 거라
돌아갈 것 같은데 인터럽트가 걸려잖아. 그럼 ISR로 가잖아 일단.
네.
그럼 거기서 컨텍스트 스위칭 먼저 한다. 엑스널리지도 안 읽고.
그러니까 읽으면 그 값을 대한 레지스터는 끝날 때까지 갖고 있어야 되는 거잖아요. 변하지 않고. 그래야 그 다음에 EOIR을 쓰기.
그렇지.
근데 그 과정에서 하려면 또 다른 뭐 스택에 푸시라고 해야 될 것 같아가지고.
그러니까 지금 그런 거는 약간의 그거는 내 반칙이네. 약간의.
그
왜냐하면 인터럽트 거기밖에 안 보인다는 거 아니까.
네,
근데 실제 시스템에서는 굉장히 많은 인터럽트가 있기 때문에 액크나로지 레지스터를 확인하지 않으면 이게 타이머 인터럽트인지 어떤 건지 모르고 타이머 인터럽트인지 알아야만 스케줄러로 점프하는 거야. 컨텍스트 스위칭을 하는 거죠. 근데 그런 로직으로 짜는 게 흐름상 맞지. 그러니까 우리가 운영 체제라든지 그런 걸 생각을 했을 때 인터럽트가 뭔지 알아야 될 거 아니야 일단. 그렇게 바꾸는 게 더
일단 수정을 해야 된다.
그게 맞는 것 같아.
알겠습니다.
돌아가는 거하고는 별개로 그래야지 소프트웨어도 아키텍처잖아.
네.
소프트웨어 아키텍처 측면에서도 그게 맞는 거지. 그냥 나는 뭐 하나밖에 없으니까 인터럽트가 그냥 이렇게 할래. 그건
알겠습니다.
이렇게. 웨이 넘버스로 그러니까 어떤 순서로 액세스 했는지를 시간 히스토리 그러니까 히스토리를 알고 싶은 거예요. 액세스 히스토리.